the correct score to be some margin above the incorrect scores, or we interpret it to be these unnormalized log probabilities. And then in this framework, we first want to get the probabilities, and then we want to maximize the probability of the correct classes, or the log of them. And so that ends up giving us the loss function for softmax. So they start off with the same way, but they just happen to get a different slight result. We'll go into exactly what the differences of them are in a bit. There are questions for now?
So these don't take significantly different amounts of time to calculate, right?
That's correct. So they take about the same time to calculate, for sure. Especially once you have a COMNET, your classifier is near instantaneous to evaluate. Most of the work is done in doing all the convolutions. And so we'll see that the classifier, and especially the loss, is roughly the same. Of course, softmax involves some exp and so on. So these operations are slightly more expensive, perhaps. But usually it completely washes away compared to everything else you're worried about, which is all the convolutions over the image. Go ahead.
What do we take log function, even if the final value tells us the probability of value? Like 0.631 is the highest number, that is more likely to be an answer. What do we take?
Sorry, I didn't catch your question fully.
Why do we have to take log function at the end?
Why do we want to maximize log probabilities instead of probabilities directly? It turns out when you, so this is partly covered in 229, when you do logistic regressions and so on. If you just want to maximize probability, it would be the exact same problem, because log is a monotonic function. And so maximizing the probability and maximizing the log probability give you the identical result. But in terms of the math, everything comes out much nicer looking when you actually put a log there. But it's the exact same optimization problem. OK, cool. Let's look at some interpretations of these two and exactly how they differ. So softmax versus SVM, and trying to give you an idea about one property that actually is quite different between the two. So they have these two different functional forms. And now assume that we have these three examples, all three examples, and suppose there are three classes, three different examples, and these are the scores of these examples. And for every one of these examples, the first class here is the correct class. So 10 is the correct class score, and the other scores are these guys, either the first one, second, or third one. And now just think about what these losses tell you about how desirable these outcomes are in terms of that W. And in particular, one way to think about it, for example, is suppose I take this data point, the third one, 10, negative 100, negative 100, and suppose I jiggle it. Like I move it around a bit in my input space. What is happening to the losses as I do that?
Like increases and decreases depending on what direction you move it.
OK. So they increase and decrease as I wiggle this data point around. Do they both increase or decrease for the third data point, for example? SVM remains the same, correct. And why is that? It's because the margin was met by a huge amount. So there's this added robustness. When I take this data point and I shake it around, the SVM is already very happy because the margins were met by, we desire a margin of 1. And here we have a margin of 109. So basically, there's a huge amount of margin. The SVM doesn't express a preference over these examples where the scores come out very negative. Then the SVM adds no additional preference over, do I want these to be negative 20 or negative 100 or negative 1,000? The SVM won't care. But the softmax could always see, you would always get an improvement for a softmax, right? So the softmax function expresses preference for, it wants these to be negative 200 or 500 or 1,000. All of them would give you better loss, right? But the SVM at this point doesn't care. And for the other examples, I don't know if it's as, that's one clear distinction, right? So the SVM has this added robustness to, it wants this margin to be met, but beyond that, it doesn't micromanage your scores. Whereas softmax will always want these scores to be, everything here, nothing there. And so that's one kind of a very clear difference between the two. Was there a question? Go ahead.
Yeah, maybe I missed this, but is the margin that 1, is that a hyperparameter? Is that something that gets changed?
Yes, so the margin of 1, I mentioned very briefly that that's not a hyperparameter. You can fix it to be 1. The reason for that is that these scores, they kind of, the absolute values of those scores are kind of, they don't really matter because my W, I can make it larger or smaller and I can achieve different size scores. And so 1 turns out to work better. And in the notes, I have a longer derivation where I go into details exactly why 1 is safe to choose. So refer to that, but I didn't want to spend time on it in the lecture.
So the notes do justify not using 0 there instead of 1?
Oh, so 0 would be, if you wanted to use 0, that would be trouble. You can use any positive number, and that would give you an SVM. If you use 0, that would look different. So for example, this added constant there, one property it gives you when you actually go through the mathematical analysis, like say in the SVM in CS229, is you'll see that it achieves this max margin property, where the SVM will find that the best margin when you actually have a plus constant there, combined with the L2 regularization on the weights. So you want very small weights that meet a specific margin, and SVM will give you this very nice max margin property that I didn't really go into in this lecture right now. But basically, you do want the positive number there, otherwise things would break. Good.
Is there a reason we're interpreting that exponential value as like the probabilities? I mean, is there a special reason we call it probabilities other than that it's non-negative?
Yeah. Is there? So you're saying we're taking this exponential of these numbers that are real numbers, and we're interpreting them as probabilities. We're kind of free to. So with this, you're getting these scores out, and it's up to you to endow them with interpretation, right? We can have different losses. In this specific case, I showed you multi-class SVM. There's in fact multiple versions of a multi-class SVM. You can fiddle around with exactly the loss expression. And one of the interpretations we can put on the scores is that they're these unnormalized log probabilities. They can't be normalized because they just can't. We have to normalize them explicitly because there's no constraint that the output of your function will be normalized. And they can't be probabilities because you're outputting just these real numbers that can be positive or negative. So we interpret them as log probabilities, and that requires us to exponentiate them. It's a very bad kind of explanation of it, but anyways. Good.
Just add on to what you just said. So that's actually pretty similar to Boltzmann statistics. If you interpret score as energy, then that's exactly the probability that energy is being occupied.
Yeah, that's right. So there are really cool connections to physics and how they actually think about the loss functions. For them, energy and loss is like kind of an equivalent as well. Good.
You're talking about the SVM versus softmax. Once it goes beyond a certain margin, like of 2 or 3, and you're going to exponentiate it, the difference you will get in softmax is going to be vanishingly small.
So you're talking about, so say for example,
yes.
In this case?
Yeah.
And now you're arguing about, say, this one?
Yeah.
Okay.
If 100 minus 100 goes to minus 110, it's still not going to really change your probabilities a lot.
That's right. So what you're saying, I think if I understand correctly, is the softmax would already look at this and give 0 probabilities here and 1 here, right? So you're saying if I jiggle this around, nothing's changing. I think the difference is the loss would definitely change for softmax, even though it wouldn't change a lot, but it would definitely change. So softmax still expresses preference, whereas SVM gets you identically 0, right?
My question is about the magnitude of that preference. Isn't it just not very big?
Yeah, so the preference wouldn't be very big, but there definitely is preference. But in practice, basically, this distinction, the intuition I'm trying to give you is that the SVM has a very local part of the space in which you're classifying that it cares about, and beyond it, it's invariant. And a softmax kind of is a function of the full data cloud. It cares about all the points in your data cloud, not just, there's like a small class here that you're trying to separate out from everything else. A softmax will kind of consider the full data cloud when it's fitting your plane, and SVM will just want to separate out that tiny piece from the immediate part of the data cloud, something like that. In practice, when you actually run these, they kind of give nearly identical results almost always. So really what I'm not trying to pitch one or the other. I'm just trying to give you this notion that you're in charge of the loss function. You get some scores out, and you can write down nearly any mathematical expression, as long as it's differentiable, into what you want your scores to be like. And there are different ways of actually formulating this, and I've shown you two examples that are common to see in practice. But and we can put down any losses for what you want your scores to be. And that's a very nice feature because we can optimize over all of it. Okay, let me show you an interactive web demo at this point. Jeffrey. All right, let's see if this. So this is an interactive demo on our class page. You can find it at this URL. I wrote it last year, and I had to show it to all of you guys to justify spending one day on developing all this. Okay. But so I'm not sure. Last year, not too many people looked at this. So okay. But basically, this is one day of my life. You should all look at this. So what we have here is a two-dimensional problem with 3 classes. And I'm showing here 3 classes. Each has 3 examples over here in 2 dimensions. And I'm showing the 3 classifiers. Here is the level set. So for example, the red classifier has scores of 0 along the line. And then I'm showing the arrows in which the scores increase, right? Here's our W matrix. So as you recall, this W matrix, the rows of that W matrix are the different classifiers. So we have the blue classifier, green classifier, and red classifier. And we have both the weights for both the X and the Y component, and also the biases. And then here we have the data set. So we have the X and the Y coordinate of all the data points, their correct label, and the scores, as well as the loss achieved by all those data points right now with this setting of W. And so you can see that I'm taking the mean over all the loss. So right now our data loss is 2.77. Regularization loss for this W is 3.5. And so our total loss is 6.27. Okay. And so basically you can fiddle around with this. So let's see. So as I change my W, you can see that here I'm making my W, one of the W's bigger, and you can see what that does in there, or the bias. You can see that the bias basically shifts these hyperplanes. Okay, and then what we can do is what we're going towards, this is kind of a preview of what's going to happen. We're getting the loss here, and then we're going to do backpropagation, which is giving us the gradient over how we want to adjust these W's in order to make the loss smaller. And so what we're going to do is this repeated updates, where we start off with this W, but now I can improve this set of W's. So when I do a parameter update, this is actually using these gradients, which are shown here in red. And it's actually making a tiny change to every single parameter according to this gradient, right? So as I do parameter update, you can see that the loss here is decreasing, especially the total loss here. So the loss just keeps getting better and better as I do parameter update. So this is the process of optimization that we're going to go into in a bit. So I can also start a repeated update. And then basically we keep improving this W over and over until our loss, it started off with roughly 3 or something like that. So now our mean loss over the data is 0.1 or something like that, and we're correctly classifying all these points here. So I can also randomize W, so it just kind of knocks it off, and then this always converges to the exact same point through the process of optimization. And you can play here with the regularization as well. You have different forms of a loss. So the one I've shown you right now is the Weston-Watkins SVM formulation. There's a few more SVM formulations. And there's also softmax here. And you'll see that when I switch to softmax loss, our losses look different. And but the solution ends up being roughly the same. So when I switch back to NSVM, you know, the hyperplanes move around a tiny bit, but really it's mostly the same. And so, anyways, so this is the step size. So this is how big of steps are we making when we get the gradient on how to improve things. So randomized parameters, we usually start with a very big step size. These things are jiggling, trying to separate out these data points. And then over time, what we're going to be doing in optimization is we're going to decrease our update size. And this thing will just slowly converge in on the parameters that we want in the end. And so you guys can play with this, and you can see how these scores jiggle around and what the loss is. And if I stop a repeated update, here's... you can also drag these points, but I think on the Mac it doesn't work. So hold on. So when I try to drag this point, it disappears. So, but it works on a desktop. So I don't want to go in and figure out exactly what happened there. But so you can play with this. Okay, cool. So I'm going to go into the process of optimization now, just to give you a sense of what this looks like. So we have this f function. We have these 2 formulations that I've shown you, and the full loss is achieved as the mean loss over data plus regularization. This is one other diagram to show you what this looks like. I don't think it's a very good diagram, and there's something confusing about it that I can't remember from last year. But basically, you have this data x and y, your images and your labels, and there's w. And we're computing the scores and getting the loss. And the regularization loss is only a function of the weights, not of the data. And basically what we want to do now is we don't have control over the data set, right? That's given to us. But we have control over that W. And as we change that W, the loss will be different. So for any W you give me, I can compute the loss. And that loss is linked to how well we're classifying all of our examples. So wanting a low loss means we're classifying them very, very well on the training data. And then we're crossing our fingers that that also works on some test data that we haven't seen. So here's one strategy for optimization. It's a random search. So because we can evaluate loss for any arbitrary W, what I can afford to do, and I'm not sure if, I don't want to go through this in full detail, but effectively, I randomly sample Ws and I can check their loss. And I can just keep track of the W that works best, okay? So that's an amazing process of optimization, of guess and check. And it turns out if you do this, I think I tried 1,000 times. If you do this 1,000 times and you take the best W you found at random and you run it on your CIFAR 10 data, test data, you end up with about 15.5% accuracy. And since there are 10 classes in CIFAR, the mean, the baseline is at 10%. That's your chance performance. So 15.5, there's some signal actually in that W. And so state of the art is at 95, which is a COMNET. So we have some gap to close over the next 2 weeks or so. So don't use this just because it's on the slides. One interpretation of exactly what this looks like, this process of optimization, is that we have this loss landscape, right? This loss landscape is in this high dimensional W space. So here I guess if you're 3D and your loss is the height, then you only have 2 W's in this case. And you're here and you're blindfolded, that's your current W. You can't see where the valleys are, but you're trying to find low loss. And so you're blindfolded and you have an altitude meter. And so you can tell what your loss is at any single point. And you're trying to get to the bottom of the valley, right? And so that's really the process of optimization. And what I've shown you so far is this random optimization where you teleport around and you just check your altitude, right? So not the best idea. So what we're going to do instead is we're going to use what I refer to already as a gradient. Or really, we're just computing the slope across in every single direction. So I'm trying to compute the slope, and then I'm going to go downhill, okay? So we're following the slope. I'm not going to go into too much detail on this, but basically there's an expression for the gradient, which is defined like that. There's a derivative, Calculus 101 definition. In multiple dimensions, if you have a vector of derivatives, that's referred to as the gradient, right? So because we have multiple dimensions, multiple W's, we have a gradient vector, okay? So this is the expression. And in fact, we can numerically evaluate this expression before I go into the analytic solution. I'll just show you what that would look like to evaluate a gradient at some W. So suppose we have some current W, and we're getting some loss, okay? What we want to do now is we want to get an idea about the slope at this point. So we're going to basically look at this formula, and we're just going to evaluate it. So I'm going to go in the first dimension, and really what this formula is telling you to do is evaluate your altitude at x plus h, subtract it from f of x, and divide by h. What that corresponds to is me being on this landscape, taking a small step in some direction, and looking whether or not my foot went up or down, right? That's what the gradient is telling me. So suppose I took a small step and the loss there is 1.25. Then I can use that formula with a finite difference approximation, where I've used a small h, to actually derive that the gradient here is negative 2.5. The slope is downwards. So I took a step, the loss decreased, so this is sloping downwards in terms of the loss function. So negative 2.5 in that particular dimension. So now I can do this for every single dimension independently, right? So I go into the second dimension, I add a small amount, so I step in a different direction, I look at what happened to the loss, I use that formula, and it's telling me that the gradient, the slope, is 0.6. And I can do that in the third dimension, and I get the gradient there, okay? So what I'm referring to here is I'm basically evaluating the numerical gradient, which is using this finite difference approximation where for every single dimension independently, I can take a small step, I can evaluate the loss, and that tells me the slope. Is it going upwards or downwards for every single one of these parameters? And so this is evaluating numerical gradient. The way this would look like is a Python function here. It looks ugly because it turns out it's slightly tricky to iterate over all the W's. But basically, we're just looking at f of x plus h, comparing to f of x, and dividing by h. And we're getting the gradient. Now, the problem with this is if you want to use the numerical gradient, then, of course, we have to do this for every single dimension to get a sense of what the gradient is in every single dimension. And when you have a COMNET, you have hundreds of millions of parameters, right? So we can't afford to actually check the loss in hundreds of millions of parameters before we do a single step. So this approach where we would try to evaluate the gradient numerically is, first of all, it's approximate because we're using finite difference approximations. But second, it's also extremely slow because I need to do a million checks of the loss function on my COMNET before I know what the gradient is and I can take a parameter update. So very slow, approximate. Turns out that this is also silly, right? Because the loss is a function of W, as we've written it out. And really what we want is we want the gradient of the loss function with respect to W. And luckily, we can just write that down thanks to these guys. Do you actually know who those guys are, by the way? Newton and Leibniz, that's right. Do you know which is which? Because they look the same. They're just, yeah, they look remarkably similar. But basically, Newton and Leibniz, sort of two inventors of calculus. There's actually controversy over who really invented calculus. And these guys fought each other over it. But basically, calculus is this powerful hammer. And so what we can do is instead of doing this silly thing where we're evaluating numerical gradient, we can actually use calculus and we can write down an expression for what the gradient is of that loss function in the weight space. So basically, instead of fumbling around and doing this, is it going up or is it going down by checking the loss, I just have an expression where I take the gradient of this and I can simply evaluate what that entire vector is. So that's the only way that you can actually run this in practice, right? We can just have an expression for here's the gradient, we can do a step, and so on. So in summary, basically numerical gradient, approximate slow, but very easy to write because you're just doing this very simple process for any arbitrary loss function, I can get the gradient vector. For analytic gradient, which is you actually do calculus, it's exact, no finite approximations. It's very fast, but it's error prone because you actually have to do math, right? So in practice, what you see is we always use analytic gradient. We do the calculus, we figure out what the gradient should be, but then you always check your implementation using a numerical gradient check, as it's referred to. So I will do all my calculus, I figure out what the loss function should be, I write an expression for the gradient, I evaluate it in my code. So I get an analytic gradient, and then I also evaluate a numerical gradient on the side. And that takes a while, but you evaluate your numerical gradient, and you make sure that those two are the same. And then we say that you pass the gradient check. Okay, so that's what you see in practice. Whenever you try to develop a new module for your neural network, you write out its loss, you write the backward pass for it that computes the gradient, and then you have to make sure to gradient check it, just to make sure that your calculus was correct. And then I've already referred to this process of optimization, which we saw nicely in the web demo, where we have this loop when we optimize, where we simply evaluate the gradient on your loss function, and then knowing the gradient, we can perform a parameter update, where we change this W by a tiny amount. In particular, we want to update with the negative step size times the gradient. The negative is there because the gradient tells you the direction of the greatest increase. It tells you which way the loss is increasing, and we want to minimize it, which is where the negative is coming from. We have to go in the negative gradient direction. Step size here is a hyperparameter that will cause you a huge amount of headaches. Step size or learning rate, this is the most critical parameter to basically worry about. Really there's two that you have to worry about the most. The step size or learning rate, and there's the weight regularization strength lambda that we saw already. Those two parameters are really the two largest headaches. And that's usually what we cross-validate over. Was there a question in the back, by the way?
I was just going to ask, is that a weight gradient vector a unit vector? Or
it's not. That gradient is just a gradient. It tells you the slope in every single direction. And then we just take a step of it. So the process of optimization in this weight space is you're somewhere in your W, you get your gradient, and you march some amount in the direction of the gradient. But you don't know how much, so that's the step size. And you saw that when I increased the step size in the demo, things were jittering around quite a lot, right? There was a lot of energy in the system. That's because I was taking huge jumps all over this basin. So here the loss function is minimal at the blue part there, and it's high in the red parts. So we want to get to the lowest part of the basin. This is actually what the loss function looks like for an SVM or for logistic regression. These are convex problems. So it's really just a bowl, and we're trying to get to the bottom of it. But this bowl is like 30,000 dimensional, so that's why it takes a while. Okay, so we take a step and we reevaluate the gradient and repeat this over and over. In practice, there's this additional part I wanted to mention where we don't actually evaluate the loss for the entire training data set. In fact, what we do is we only use what's called a mini-batch gradient descent, where we have this entire data set, but we sample batches from it. So we sample, say 32 examples out of my training data. I evaluate the loss and the gradient on this batch of 32, and then I do my parameter update. And I keep doing this over and over again. And basically what ends up happening is if you only sample very few data points from your training data, then your estimate of the gradient, of course, over the entire training set is kind of noisy because you're only estimating it based on a small subset of your data. But it allows you to step more. So you can do more steps with approximate gradient, or you can do few steps with exact gradient. And in practice, what ends up working better is if you use mini-batch. And it's much more efficient, of course, and it's impractical to actually do full batch gradient descent. So common mini-batch sizes, 32, 64, 128, 256. This is not usually a hyperparameter we worry about too much. You usually set it based on whatever fits on your GPU. We're going to be talking about GPUs in a bit, but they have finite amount of memory, say about like 6 gigabytes or 12 gigabytes if you have a good GPU. And you usually choose a batch size such that a small mini batch of examples fits in your memory. So that's how usually that's determined. It's not a hyperparameter that actually matters a lot in optimization sense. Go ahead.
If you wanted to use momentum on the step size, could you still do it with the mini batch update?
Yeah, for sure. And we're going to get to momentum in a bit. But if you wanted to use momentum, then yeah, this is just fine. We always use mini-batch gradient descent with momentum. Very common to do. So just to give you an idea about what this looks like in practice, if I'm running optimization over time, and I'm looking at the loss evaluated on just a small mini-batch of data, and you can see that basically my loss goes down over time on these mini-batches from the training data. So as I'm optimizing, I'm going downhill. Now, of course, if I was doing full batch gradient descent, so this was not just mini batches sampled from the data, you wouldn't expect as much noise. You just expect this to be a line that just goes down. But because we use mini batches, you get this noise in there because some mini batches are better than others. But over time, they kind of all go down over time. Is there a question?
Outside of curiosity, should the graph look like it decreases greatly in the beginning and slowly decreases?
Yeah, so you're wondering about the shape of this loss function. You're used to maybe seeing a more rapid improvement quicker. These loss functions come in different shapes, sizes. So it really depends. It's not necessarily the case that a loss function must look very sharp in the beginning, although sometimes they do. They have different shapes. For example, it also matters on your initialization. If I'm careful with my initialization, I would expect less of a jump. But if I initialize very incorrectly, then you would expect that that's going to be fixed very early on in the optimization. We're going to get to some of those parts, I think, much later. I also wanted to show you a plot of the effects of learning rate on your loss function. And this learning rate is the step size. Basically, if you have very high learning rates or step sizes, you start thrashing around in your W space. And so either you don't converge or you explode. If you have a very low learning rate, then you're barely doing any updates at all. So it takes a very long time to actually converge. And if you have a high learning rate, sometimes you can basically get kind of stuck in a bad position of a loss. So these loss functions you need to get down to the minimum. So if you have too much energy and you're stepping too quickly, then you don't allow your problem to kind of settle in on the smaller local minima in your objective. In general, when you talk about neural networks and optimization, you'll see a lot of hand waving because that's the only way we communicate about these losses and basins. So just imagine like a big basin of loss, and there are these like smaller pockets of smaller loss. And so if you're thrashing around, then you can't settle in on the smaller loss parts and converge further. So that's why learning rates is no good. And so you need to find the correct learning rate, which will cause you a lot of headaches. And what people do most of the time is sometimes you start off with a high learning rate, so you get some benefits, and then you decay it over time. So you start off with high, and then we decay this learning rate over time as we're settling in on a good solution. And I also wanted to point out, we'll go into this in much more detail, but the way I'm doing the update here, which is how do you use the gradients to actually modify your W? That's called an update, a parameter update. There are many different forms of doing it. This is the simplest way, which we refer to as just SGD, simplest stochastic gradient descent. But there are many formulas such as momentum that was already mentioned. In momentum, you basically imagine, as you're doing this optimization, you imagine keeping track of this velocity. So as I'm stepping, I'm also keeping track of my velocity. So if I keep seeing a positive gradient in some direction, I will accumulate velocity in that direction. So I'm going to go faster in that direction. And so there are several formulas. We'll look at them shortly in the class, but AdaGrad, RMSProp, Atom, all commonly used. So just to show you effect of different what these look like, these different choices, and what they might do in your loss function. This is a figure from Alec. So here we have a loss function, and these are the level curves. And we start off optimization over there, and we're trying to get to the basin. And different update formulas will give you better or worse convergence in different problems. So you can see, for example, this momentum in green. It built up momentum as it went down, and then it overshot, and then it kind of goes back. And this SGD takes forever to converge in red. That's what I presented you so far. So SGD takes forever to converge, and there are different ways of actually performing this parameter update that are more or less efficient in the case of optimization. Yeah. So we'll see much more of this soon. I also wanted to mention at this point, slightly shifting gears, I wanted to go slightly into, I've explained now basically linear classification. We know how to set up the problem. We know there are different loss functions. We know how to optimize them. So we can kind of do linear classifiers at this point in the class. I wanted to mention that I wanted to give you a sense of what computer vision looked like before COMNETs came about so that you have a bit of historical perspectives. Because we used linear classifiers all the time. But of course, you don't use linear classifiers on the raw original image because that's a pixel. You don't want to put linear classifiers on pixels. We saw all the problems with it, like you have to cover all the modes and so on. So what people used to do is they used to compute all these different feature types out of images. And then you compute different descriptors and different feature types, and you get these statistical summaries of what the image looks like, what the frequencies are like, and so on. And then we concatenated all those into large vectors, and then we piped those into linear classifiers. So different feature types, all of them concatenated, and then that went into linear classifiers. That was usually the pipeline. So just to give you an idea of really what these feature types were like, one very simple feature type you might imagine is just a color histogram. So I go over all the pixels in the image, and I bin them into, say, how many bins are there for different colors, depending on the hue of the color. And so you can imagine this is kind of like one statistical summary of what's in the image. It's just the number of colors in each bin. So this would become one of my features that I would eventually be concatenating with many different feature types. Another kind of, and so basically the classifier, if you think about it, the linear classifier can use these features to actually perform the classification because the linear classifier can like or dislike seeing lots of different colors in the image with positive or negative weights. Very common features also included things like what we call sift and hog features. Basically, these where you go in local neighborhoods in the image, and you look at whether or not there are lots of edges of different orientations. So are there lots of horizontal edges or vertical edges? We make up histograms over that. And so then you end up with just this summary of what kinds of edges are where in the image, and you concatenate all those together. There was lots of different feature types that were proposed over the years. Just LBP, text-on, lots of different ways of measuring what kinds of things are there in the image and statistics of them. And then we had these pipelines called bag of words pipelines, where you look at different points in your image. You describe a little local patch with some scheme that you come up with, like looking at the frequencies or looking at the colors or whatever. And then we came up with these dictionaries for, okay, here's the stuff we see in images. Like there's lots of high frequency stuff or low frequency stuff in blue and so on. So you end up with these centroids using k-means of what kind of stuff do we see in images. And then we express every single image as statistics over how much of each thing we see in the image. So for example, this image has lots of high frequency green stuff. So you might see some feature vector that basically will have a high value in high frequency and in green. And then what we did is we basically took these feature vectors, we concatenated them, and put a linear classifier on them. So really, the context for what we were doing is as follows. What it looked like mostly in computer vision before roughly 2012 was that you take your image and you have a step of feature extraction where we decided what are important things to compute about an image. Different frequencies, different bins, and we decided on what are interesting features. And you'd see people take like 10 different feature types in every paper and just concatenate all of it, just dump all of it. You end up with one giant feature vector over your image, and then you put a linear classifier on top of it, just like we saw right now. And so you train, say, a linear SVM on top of all these feature types. And what we're replacing it, since then, we found that what works much better is you start with the raw image, and you think of the whole thing. You're not designing some part of it in isolation of what you think is a good idea or not. We come up with an architecture that can simulate a lot of those different features, so to speak. And since everything is just a single function, we don't just train the top of it, on top of the features, but we can actually train all the way down to the pixels. And we can train our feature extractors effectively. So that was the big innovation in how you approach this problem is we try to eliminate a lot of hand-engineered components, and we're trying to have a single differentiable blob so that we can fully train the full thing starting at the raw pixels. So that's where historically this is coming from and what we'll be doing in this class. And so next class, we'll be looking specifically at this problem of we need to compute analytic gradients. And so we're going to go into backpropagation, which is an efficient way of computing analytic gradient. And so that's backprop, and you're going to become good at it. And then we're going to go slightly into neural networks. That's it.